Okay, so thanks. Really happy to be back here at Imperial College. Yeah, asked AI to generate me a picture of FPGAs in London, and that was the best it could come up with. But I like to tell a crone. I don't know what we're gonna call her and tell her, but we're gonna tell a crone. The AI era. So this is kind of important guy at Microsoft I like to keep happy. And he's declared this to be the AI era, so it must be true. Said in his lifetime, he's seen two demonstrations of technology that really struck him as revolutionary. The first in 1980 was the GUI, and that basically led to Windows. The second came in just last year with AI, and you can check that with Gates' notes. That actually, follows what I think most people know, because it went mainframe to PC, and then Gates missed a couple of eras, and now it's AI. So if you think of the computing edition, of the eras to where it's really, mainframe, PC, mobile, cloud, and now kind of AI. But if you think of it for FPGAs, it's a little bit different. It's ASIC prototyping was the big thing for quite a while, and then networking and telecom. Then we went into really specialized compute, and then we went to cloud and AI. That's a little funny, because what really has made FPGAs successful in the past is being one of two things, maybe both. Being first, which is really what helped them in the networking and telecom space. They always had the best transceivers, the fastest. They were there before any of the standards were finalized, so they could get there before any of the ASICs could. Or they're special. They do a job that nobody else either wants to do or can do at an economically viable kind of point in the spectrum. And the thing about this is we've actually had a bit of a change in the last AI era, because first could be one of two things. It could be first in silicon, or it could be first in algorithm. Part of the reason FPGAs were often first in silicon is that they're very regular. They have cutting edge IO demands, and they're a reliable market for early silicon. Problem is, there's a much more reliable market for early silicon that is incredibly regular and has cutting edge IO demands. And so the AI era has kind of stolen all that thunder. So for the FPGAs, they're not going to be first to market in silicon anymore, for the most part. And if you're specialized in algorithm, well, that's really, first in algorithm is really just another kind of extension of being special. So in the end, it's really, can they compete when the biggest players in computing are focused on the same things as FPGA researchers and developers? You can if you're first, and you can if you're special. And really, that just means you got to be special. So here's the two kind of target markets, and where Microsoft has put their efforts in these last two spaces. So in the cloud and data center space, it's been in Azure Accelerated Networking, which is now, like, its public name is Azure Boost. And in the AI ML space, it's with Project Brainwave. And so we kind of dive in here. There's another important Microsoft guy I'd like to keep happy. And he's there displaying Azure Boost. And basically, this is our networking and storage acceleration card. This is a variant of this, or its predecessors have gone into every single server that we've shipped at Microsoft since 2015. And if you've looked at the number of servers we've shipped since 2015, that's a lot. However, it doesn't seem to have actually helped. When they named it Azure Boost, it turns out that was also a sneaker by Yeezy, by Jade. And so even now, that's usually what Bing thinks when it finds Azure Boost. But don't be fooled, it's not just Bing. Google doesn't do a much better job. So A+ on the marketing guys who nailed that one. Like, I guess they don't do a Google search when they come up with A. Come on, guys. All right, and so we announced the general availability of Azure Boost just pretty recently, the 200 gig generation. One of the cool things about this, underneath that board, you can take the heatsink off and see a bunch of things like this. Here's one of the keys to getting a project through Microsoft. See that in the middle there? It's called Celestial Peak. And Celeste is my daughter. Nobody wants to cancel a program named after a child. So Azure Boost, what was really special about it? Well, it regained our dominance in both networking throughput and in storage throughput, but it didn't do it right from the start. When it first came out, basically before, this is our performance, but in the very first release, it's got the second graph. But we kept building, kept adding new things, kept adding new features. and got the performance way, way beyond what it was. So this allowed us to basically jump out there and not only regain the performance lead, but to continue to build on that lead after it had already been shipped. And a lot of the features that we developed for this, we can push back into the existing fleet, into other FPGAs that are already out there, and improve the experience well after we've shipped the silicon. It's similar to what we did in the 40G generation, where we basically quadrupled the performance, 4x faster, a whole bunch of new features, and in the end actually reduced the number of FPGA resources because we're optimizing and optimizing as it goes. What about the AI ML space? So Project Brainwave was one we started back in 2015 as part of Bing. It's actually really just an extension of Catapult. And what is really special about Brainwave? Well, the basic idea behind it was we pin all these weights to these distributed memories that are all over the FPGA fabric, and we flow the data basically in a data flow fabric. Not quite like the thin stuff because it's not that thin, but it's more a soft NPU kind of architecture. And did a bunch of optimizations for low batch size. One of the reasons at the time that Bing wasn't really using GPUs that much is because their performance on batch size 1 wasn't that good. And what that meant is they batched up lots of queries to get the throughput you needed. Problem is you don't want to wait for 250 other people to do a web search before we start working on yours. We're only doing one at a time. And so there's lots of optimizations around low batch size. And then you would spread larger and larger neural networks out across multiple FPGAs. And in order to really make the most of that, we also did a bunch of custom RDMA-like transport protocols for the network to make sure that things went really fast. And finally, we did custom data types for really efficient inference. This is sub 16-bit, even sub 8-bit floating point standards where you're basically sharing some of the bits, and then you can make a very, very efficient use of this. And this is one of the kind of secret sauce things we had at the time that we released Brainwave. So the thing is, we've been around long enough and been chasing this AI wave for quite some time. In fact, the entire origin of the FPGA program at Microsoft was because Bing was too slow on walking boosted decision tree forests, which were the pinnacle of AI at that time. So we made the entire board, everything we had there was actually started to walk decision trees quickly. We never put that in production, but with the exact same hardware, we made it do CNNs, later LSTMs, and transformers, all with the exact same hardware that we had developed before. So that's a lot of new tricks. There's another favorite of my AI generated. It went from boosted decision tree forests to convoluted neural tree forests. I'm like, yeah, that sounds about right too. The thing is, we're probably not done evolving this. The transformers are huge, but there's still a lot of other areas where this innovation can go. And so, the FPGA might be, in a good position if the algorithms change a lot. And in fact, this became the largest deployment of AI FPGAs, for quite some time. We wrote about it in ISCA 2018. But one of the cool things about the last ISCA, ISCA 50, was that they invited retrospectives for several of these papers. And we did a retrospective on this one and said, basically we've done a whole bunch. We, still run it on Stratix 5, which was the original FPGA we deployed back in 2015. Run it on ARIA 10, on Stratix 10, even had a custom version of Stratix 10 created, and did a whole bunch to do that. Even today, Bing still uses these, quite a bit. But part of this, we talked about some of the pitfalls, and in particular, the GPUs are just moving really, really fast. They incorporated HBM, and even though we got a custom FPGA with it, HBM and support in the DSP units for this, ultimately, it was the hardware lottery that made GPUs really good. And with the hardware lottery, basically the term is that, when hardware is available, when researchers start using that and when developers start using it, it may not actually be the best hardware out there, but if it's available, they start customizing to that. And then the more you customize to that, they start actually thinking in the paradigms of what that hardware supports. And in the large way, that's exactly what the GPUs have done. And that's the transformer models map very, very well to GPUs. And because they map to all the GPUs, we're buying more GPU hardware. And because we have more GPU hardware, we're going to keep trying to map things nicely onto GPUs rather than really try to find other ways to do this. So unless there is a far more seismic transformation than the ones that have happened before, it's likely for this kind of scale and class of workload, the GPUs are going to be the right choice. Here's another way to think about or illustrate the hardware lottery. So you got kind of 4 quadrants. GPU as your hardware architecture, or a different and alternative custom architecture, and CUDA as your library or a custom software stack, kind of other. Obviously, there's only one member of that quadrant. That's a happy quadrant to be, because those trillions of dollars just keep coming in. They can't cash our checks fast enough. That's a good place to be. AMD, they acquired ATI years and years ago. ATI was a GPU competitor to NVIDIA. Their hardware is largely the same. Like, there's not really a lot of fundamental differences between them, but the software stack it's different. And if you think of the enormous lift it is for AMD to be able to run the same kind of stuff that is even running on NVIDIA, that's a huge initiative for them. They're pushing very hard in that direction, but it's not easy. Well, why don't we just have, there are implementations of things that run CUDA but are custom architecture. They're mostly implementations that are submitted to Hotcrap or in Excel. So, okay, those are academic papers. That quadrant doesn't really exist. And then there's this very crowded, there's this very crowded corner down here, which is we've made our own AI accelerator. We've made our own chip. Isn't it going to be awesome? And the problem is, not only are you trying to fight the software stack problem, you're trying to fight the architecture problem. Here's the insight that really makes it tough to catch up in this space. When a new paper comes out in NeurIPS or ICML, the top machine learning conferences, they're generally done on NVIDIA hardware, which means the day that comes out, they release their code, they release the idea. NVIDIA can take that code and run it on NVIDIA hardware that day. They can prove the results. They can play with that. Not only that, they can project it to GPU generations that aren't public anymore. So the day that paper comes out, they now have more insight into that research paper than the researchers themselves. Now look at what the other folks have to do. You have to at least port the software. And if you have to port the software and the architecture stack, that puts you behind a serious 8 ball. So is Bing still using FPGAs? Yeah, but they're using GPUs a lot more. Brainwave is actually still, even to this day, competitive, although generally a bit inferior on performance metrics compared to GPUs. But it is superior on metrics when overall cost is included. So that's kind of where we sit for Microsoft's entries in this. So what about the rest of the non-Microsoft world? Well, in AI and ML, that space is just really evolving too quickly for most people to care about hardware innovation. And I know this is really sad for all the AI chip startups out there, but it's really hard to hit a moving target that's going that fast with innovative hardware. And it's also not clear how we make money on the mainstream, much less on an optimization of the mainstream. I mean, while this is the AI era, there is one clear winner in the AI era, which is NVIDIA. We still haven't quite figured out how we're going to make money on this stuff. We're still doing it. We still think it's important, but honestly, we don't know how we're going to make money. And FPGAs didn't win the hardware lottery, so it's unlikely there's going to be a ton more investment in that space in the near term, unless you can find something different. Same thing, and I'll save this for a different talk, but basically, why aren't there lots of FPGAs all over the other hyperscalers? Well, customers don't actually want you to differentiate. One of the biggest reasons that people use Azure is because they're using AWS, and they want to be able to tell Amazon that we have another cloud. And so if we produce something for them that's special to us, they usually say, okay, this is great. How do I move it on to Amazon? You're like, that's not what made it for you. But hey, and the lack of common shells, tools, tool flows, things like that make portability really difficult. So even if we wanted to let the customer be able to do that, it's really hard to get stuff up and running. And that's a place that I know there is some research and there's a lot of good ideas floating around, but that's a place where kind of the community still needs a lot of extra work. And for the most part, the third-party FPGA programs for the FPGA for rent largely have kind of failed. And for a variety of reasons I'm happy to go into sometime. So can FPGAs compete when the biggest players in computing are focused on the same thing? As I said, yeah, let's go back to this be special thing. So go be special, but not too special. Also, what is special? So let's try to define what special is. Like special is more than what gets you published. So what gets you published? Performance, power, performance per watt, maybe performance per dollar, maybe performance per watt per dollar per paper average review. Let's make up a metric where we're superior on something. But the thing is, it really includes anything that also has impact. So it's the relevant application layer kind of stuff that you're going to see. It's not about flops. It's not about ops or even inferences per second on NMIST. Sorry, okay. What does the customer actually see and experience? And here's a point that I just beat my, beat the drum over and over and over. It's very hard to lead in the cloud and hardware. If it was about the hardware, if it was about your performance per watt, if it was about that hardware widget, who would have the biggest clouds on the planet? Huawei, Intel, NVIDIA, Samsung, AMD. Who has the biggest clouds on the planet? An online book reseller. The people who brought you Microsoft Teams, Skype, search engines, online eBay, basically eBay in China. They're the ones who have brought you the cloud. Why is that? That's because they're the ones who are interacting directly with the customers. They're the ones who follow what the customers want. They're the ones who the customers give the money to. And the hardware is on the back end. It's not what they see. It enables, but it is not the leading thing. So the idea is focus on what the customers are seeing and understand the customer experience. Jeff Bezos would be proud to hear me say that. A few other major concerns when you're kind of dealing with this thing. Everywhere and nowhere. Until an accelerator is in every relevant region, software has to have two branches, the with accelerator and the without accelerator. Now, Git exists as a source repository, mostly because what's the favorite thing for software engineers to do? Branch. We love to branch. We love to fork off new branches. Problem is, if you inherently have two branches, those are going to continue to branch. Now, what's going to happen is it's going to be very, very difficult to keep them up to date. And software developers like to work on, the main branch. What is going to be the main branch until they're everywhere? The no accelerator thing. So even if you have the coolest, newest, greatest little features on your hardware, until it's managed to roll out worldwide, it's going to be very hard to get the software people to use it. And because this is worldwide, this is very large, this takes years. So even the cool new, thing, this is hard for startups to deal with because they're like, I've got startup funding to last another year. You're like, it'll take me way longer than that to get this thing out, even if I really do want it. So Azure's got 65 plus regions and growing. The thing is, because of these branches and because of the different hardware, going back to that customer experience, they're not going to have a consistent experience. And one of the things that I learned being in the product teams after I jumped out of research is customers not only don't like an experience if it's worse than they were expecting, they actually don't like it if it's better. So this is basically a real scenario we had where there's a global, large scale corporation you've probably heard of, Walmart. But basically what was happening is we accidentally turned on accelerated networking when it was still a preview feature in one of their regions, one of their data centers. It made that one run 4x faster than all of the other regions. They were complaining because they really thought the other regions were running slower. And even when they figured it out, they weren't happy about it because they didn't want one customer to go one day and have one experience and the next day come and have a different experience. And so when companies are putting together things and they're trying to decide how they, how many virtual machines they allocate, whatever they do it to, make sure customers have a good experience. And they're actually not happy if one thing goes fast and one thing goes slow. And so again, this pushes product teams towards the no accelerator branch, don't use the new hardware. So what's special? Make your designs work with old and new hardware. Because the more that you can push it out to stuff that's already out there, the more of a chance you're going to get those folks to jump onto the with accelerator branch. Another kind of special feature, allowing experimentation. So the Bing Accelerator began, as I said, scoring boosted decision tree forests. We started out with a 250x, improvement in speed up. But software doesn't sit still. That was in February. By March, they had improved it by over 10x. We were still faster, 31, but not quite the same. And we improved a little bit more. But, we had to basically keep adapting to what they were doing and allowing experimentation, trying to add new features, trying to add new things. And one of my favorite quotes here is, Andrew, even if Catapult never shipped a single FPGA into production, you've had a major impact on the performance and relevance of Bing. And the reason is I was running around Bing, shaming their poor developers and like, hey, you have the slowest portion of Bing. What's wrong? And I actually did that to my friend Kyle Allahan, and I did it on a Thursday, and he told me, oh, wait, I'll get you the documentation, whatever. I'll have it for you on Monday. It's Thursday. I was like, yeah, no problem. He went on a, Red Bull infused, Red Bull and pizza infused hackathon that weekend and came out on Monday. And instead of sending me that, he's like, I improved the performance by 25x. I'm like, dude, what am I going to do now? Putting myself out of a job. And another special one, adapting for multiple program phases. This man is a computing pioneer, but everybody in here should hate him because he is the ruiner of accelerator dreams. The code you accelerate is only part of the full algorithm. That 100x becomes 2x very, very quickly or less. What you often need is tightly integrated CPU platforms. In particular, and even in this cool AI era, GPU SKUs are 17x or more expensive than comparable just tool socket CPU platform in terms of how much it costs you to rent it. If you're not actively using every ounce of that GPU, you do not want to be on that platform because it's costing you a ton. So if you look at cloud scale workloads, none of those look like, and this is actually Bing, a profile, none of that is 90 to 99% of the CPU utilization. That thing's bouncing all over the place. So if you're only going to pick one thing to accelerate, at best, you're not even going to get 2x there. So you've got to adapt to multiple program phases and find more tricks than just one to accelerate, because that's by far what most of these cloud workloads look like, even in the AI era. One of my favorite use cases for this, which Michaela also brought up, the CERN folks who do the particle detection. They actually have the AI embedded in their data acquisition pipeline. So they're finding a way where it's like the rest of their program is basically about data acquisition. They found a way to do the data acquisition and the AI AI in the same chip. That's pretty cool. Finally, a big one that's on people's mind. Let's be green. We want to be ecological. We need to do that. How can we be special here? Microsoft pledged to be carbon negative by 2030. Actually, those are more people who I'd like to keep happy. Her in particular, she's our CFO. She writes the paycheck. Keep her happy. We said we'd be carbon neutral by 2030. That was basically the plan in 2020. Need to hit that black line. Where are we? Oops. This came out. We're up 29.1%. Why? Basically, primarily comes from construction of more data centers associated with embodied carbon that's there. We're building AI. This doesn't even count the data center supercomputers that we're building for AI now, which is going to make this way, way worse. But understanding why is really more like this. What's better for the environment? Should I go buy a Tesla? That's my car. No, it's a 96 Mustang Cobra. It turns gas into heat and noise. But is it a good idea to go buy a Tesla? Well, it turns out it's more than performance and power efficiency, because the right thing to do is actually to drive this car into the ground and then go buy a Tesla, because the amount of carbon that it takes to produce the battery and the rest of that Tesla wildly overshadows the savings that you're going to get, compared to that. So if you've, if you can run into the ground and buy a Tesla, that's the right thing. The other thing is try to find other things to do with that. And those are all very real pictures. They're about the dining room table home, the TV, that was me moving offices. So just be creative. There's more to being special in performance and power efficiency. And just the last thing, especially here, which I thought, can grad students really have a big impact? It turns out that I was only out of grad school for a year when we started the Catapult program. And this is a great ramp retreat from 2007 down at UT, and ramp, like this kind of legendary FPGA research program from these various universities. In this picture, partner engineering manager, fourth employee on Catapult, principal engineer, the ASAP, the storage accelerator lead developer, joined in 2012, 2013. This guy just left Microsoft a few months ago, now the vice president of AI at NVIDIA, fifth employee on Catapult. And the Mango Boost co-founder, I don't know how we didn't get him at Microsoft. And of course, me. So basically the key message, we started in 2010. It was developed by grad students who were just a year or two out of graduation. And it really worked because grad students cross disciplinary boundaries better than anybody. Why? Because professors are cheap and they're not going to buy you that professional developer, or they're not going to buy you the nice cases. You got to go build it yourself. And I think with the work that you're all doing here, you really do have a chance. You don't have to wait 20 years. You don't have to wait 10 years into your career. A lot of the opportunities here, because the space is moving so fast and so quickly, you're going to be the best people to do this, because the people who've been in industry too long get set in their ways. You're going to see paths forward that just don't exist in other places. So in conclusion, FPGAs compete by being first and special. And okay, I'll say just special. Cloud and AI markets are large enough to compete on both metrics faster than FPGA hardware alone can evolve. Competing head on isn't what has made FPGAs successful historically. And there's more to being special than power, performance, cost. So embrace backwards compatibility, but think of what customers want. There's simultaneous hardware and software generations out there, worldwide deployment. You got to have more than one trick. And the impactful metrics come from adaptation as much as they come from any amount of power, performance, or cost. So that'll take questions.
Thanks, Andrew. Great talk. So I think I saw a New York Times article that said that the amount of energy or power that we're using for AI is equivalent to the Netherlands on average. And I think we're going to get more in the public consciousness about the huge energy costs of it. So, and you talked about power, but maybe we need to emphasize that metric a little more. And maybe it's going to be, right now, I don't think you can make money by saying you're more energy efficient than GPUs with FPGAs, but I think there may be a day when we can. So in my group, we wrote some papers showing that FPGAs are more energy efficient than GPUs on a number of tests. So is that something you looked at in your experience, specifically the power consumption, energy efficiency, FPGA versus GPU?
Yeah, so we can make some of those claims because Bing has been looking at that a bunch, not just cost, but power, which actually kind of feeds into cost. Right. There is a huge difference in the amount of power generated. It's crazy to spend these gigantic transformer models on some of these tasks. There's an amazing paper from Kim Hazelwood at Facebook, HPCA 2018, that talked about the machine learning models that they used at Facebook. She said, what do you think we use for these? Is this your friend, Michaela, in the photo? Like, we don't use the latest, greatest CNN, like 8 billion compute cycle, algorithms, because we're not trying to match that to any person on Earth. We're trying to match that to a friend you have, which is, let's say, 200 people who, might be about the same time and place as you, which usually is actually selecting between about 6 people. And so right sizing your algorithms to what you do is a huge thing that we can kind of do. The other piece about that is we don't have good metrics for how you take adaptability and convey that into some kind of carbon or energy savings. But the fact is, if you make your hardware last an extra year, that was far more important than if it was 10% more energy efficient. And one of the things that scared me about the AI models and the GPUs we're doing now is hardware is not lasting longer. The hardware cycles are getting shorter. So we've already made big assumptions about these GPUs that we're pulling in now and buying are going to last 6 years. But are they? Because every one of the product teams at Microsoft is saying, I'm starved for GPUs. I don't have GPUs. I don't have GPUs. We have V100s all over the place 2 generations ago. You're like, hey, you want those? Like, well, nah. I want the new one. And so if they don't actually last 6 years, the energy cost is going to be even worse than what we're projecting. And so I think at some point that's going to catch up, and energy efficiency and your ability to just last and be useful longer is going to be increasingly important.
And I think in the meantime, that the messaging is important, right? Get the word out that there is an advantage and it's going to have an impact on the world if we use the A100s instead of the.
Yeah, that's huge. Well, the funny thing is you get beat up from the ASIC side, like the other vendors who are like, oh, we're custom, like don't go with the FPGA, go with this custom thing. You're like, yeah, but now we've got the same problems. What's the useful lifetime of that going to be if the algorithms adapt very much?
I think in the interest of dinner, we may call it there and please have questions for Andrew afterwards.
All right, I didn't think I was going to ruin your dinner with it.